Good afternoon. My name is Seif Azghandi. I'm with Air Force Institute of Technology in Dayton, Ohio. I work with Dr. Hopkinson, and who couldn't be here, unfortunately, due to sequestration. So, just to give you a little background here, we recently submitted a paper in regard to distribution, more specifically about smart meters, and that dealt with the security and what have you. So when the sequestration happened, I guess Dr. Hopkinson asked me that if I can come and present from his behalf. This is a long way of saying that I'm new to power grid. So I'm basically learning the alphabets of the power grids. So with that in mind. So motivation here, of course, we need a fast response from our communication system. We can't afford personal injuries. We need we can't get the system disrupted because it's going to cost a lot. And of course, we can't find individuals who are both fluent in SCADA and the security both. And basically, and then of course, I'm pretty sure we can just think about more reasons why we have to go after the control, protection in the control system. So stress on power grids, population grows and continually more demand for power, but the communication infrastructure cannot keep up with it. So if you think about the next generation of the utility intranet, we can look at the 61850, UCA and WAMS and ASPE. We see that we are really going toward a wide area management, wide area measurement system. So that's up and coming. Of course, motivation is that preventing cascading outages and investigate the trade-off in communication-based power protection and control. Because obviously we have to pay some price and gain some benefit out of it. This is a busy slide, and it deserves a couple of minutes of talking about this. This is the EPOCHS, which stands for Electric, Power, and Communication Synchronizing. Synchronizing Simulator. It took me a while actually, to learn this, acronym. So basically, it's a simulation, program, or an environment rather. As you see that, we have brought in 3, commercial off-the-shelf, simulators, which is Network Simulator 2, which is open source. We have a PSLF, which deals with the electromechanical systems. We have the PSCAD/EMTDC, C has dropped out, which is the electromagnetic system. And so you push them together, basically, we should be able to synchronize the system. Now, RTI stands for runtime infrastructure, which its job is that to get the inputs from these 3 simulators and sequence them and pass it along to a whole bunch of agents. And of course we have a unified views for all the agents, so we can imagine that all the agents are under one umbrella. The agents are the one that do the actual work, and agents are all software based, and they have ability to intercommunicate with the other agents. They reside in intelligent electronic devices, IEDs. Usually when you run the simulation, NS2 works with PSLF or PSCAD individually. We have not been able to run this system with all the 3 pieces simultaneously. And the reason for that is because PSCADs, I believe, deals in microseconds, and PSLF deals in just milliseconds, so there's a variations in the time here. Here's a backup protection system that we're dealing with, and basically what you see on the left side here, it says that without agent base, we might have the disturbance persisting for a long time. And on the right side, what we see is that with agents, intercommunicating with the other agents, we would have a shorter, disturbance. And of course, based on the, simulations, the system response has improved by 87%. So, and it in fact it shows that how the breaker in 5 or the actual, fault, starts communicating back to B3, and it catches it. So I guess agents are basically faster. Here's the remedial access or remedial access system, I believe. And we see that in the heavy summer heat, we could have the power flowing both back and forth. And RAS, by the way, and SPS are the same. Here it is, when a disturbance occurs, maybe due to load shedding, and the whole point is that bringing the frequency up to a preset value or a stable system. And what you see with the equation above is the disturbance on the left side, and it's a function of functional acceleration of the power through the system, and of course the difference in the with respects to the frequency and the voltage. What you see as the pluses and minuses are the system before and after the disturbance. And basically it says that the counteracts and stabilize the power system, perform generator rejection, load shedding, and faster information updates. So here's the 50 generated IEEE test case. If you see the one on the right, the simulation, take the other parameter, basically just goes around right here, which is high voltages, and it captures it right there. And what you see, the red line is perhaps a fault. Here's the frequencies of southeast system through the remote load shedding. And what you see on the right side is that preset frequency to 58.8. Here's a background traffic that we've been kind of wondering about. It's the based on the SCADA constant and rate packet size. And what you see in the bottom here is time between bursts in milliseconds, old and new values. Again, with the traffic types. Here's more information here. We're using the UDP and the TCP communication protocols. And on the left side, you see a bunch of information about the bandwidth, delays, and background traffic through the UDP. The shortest path in PPRN, which is the research network, I forgot the PPRN, but it's the, never mind, let's skip that. So here's the simulation type, all traffic loads. We have the shortest path, we have no reservation, and we have reservations, or rather reservations, on the top and in the bottom. And he shows the shortest path in PPRN, basically. Kind of looks similar here. So, summary of the traffic load here is that the UDP, of course, runs faster than TCP because TCP is acknowledgement. And rather middleware, reservation performance lot. they are equal with the UDP reservations. And of course, PPRN, performed a little better under medium and heavy background traffic. So now hypothesis, we were thinking that if we incorporate exponential weighted moving average in the buffer scheme, we can compensate for the packet loss to the competing network. Here's actually the next 4 slides that's going to show the results. We see that under heavy traffic, the next slide is under medium traffic, we see quite a bit of a difference here. So it seems like exponential weighted moving average is doing definitely better than without this exponential moving weighted average. So that's a better choice. Next slide again with the medium traffic is the same deal more or less. And here we see this with the live traffic, and of course that's expected. We see that 2 graphs are basically just touching almost. So we see that it's not going to make all that much of a difference. So conclusion here is that I think the power grid and communication scheme holds a great promise. The EPOCHS system will be critical actually to evaluating protection schemes. And it shows that agents are quite valuable in incorporating it into a system, so the software will do the job. At the end, I just want to thank Dr. Thorp and Dr. Phadke here, and I appreciate the opportunity. And as I said, that regretfully, Dr. Hopkinson couldn't be here in person. He would have been a right person to just present and just be part of this. Thank you.